right side of AB. Okay. So we have to find all limit points. Okay. So that is, we have to find all limit points of open interval. So you start with a point inside AB, let x belongs to AB, and we will show that this x is also a limit point. So AB, in geometrically you can represent it this way. So if I take a point x inside AB, okay, what is the limit point? Every epsilon neighborhood of x should contain at least one point of this set different from x. Okay. So let us consider an epsilon neighborhood of this x. So let epsilon greater than 0 be given. So this epsilon may be large also. Epsilon is if epsilon is large, okay, then see, so many points are included. If epsilon is small, okay, somewhere here, then also some points are included. Okay, so we need to find at least one point which is different from x. Okay. In the interval x minus epsilon to x plus epsilon. Okay, in that interval we need to find out. So if this happens, epsilon greater than 0 be given. Okay, I need to find at least one point inside x minus epsilon to x plus epsilon. So we have if A is greater than x minus epsilon. Okay, so it may happen that x minus epsilon is somewhere here. Okay, it may happen like that. X minus epsilon may be somewhere here. Okay. So in that case, what we can say, we will consider one point, okay, inside this. Okay. How to consider one point inside this? X plus, if x minus epsilon is less than a. Okay, so that means I have to consider points which are greater than a. Okay. If I consider points which are less than a, those points will not lie inside the set AB. Okay. I have to find points which are lying inside the set capital A, here this AB. Okay. So let x belongs to A. If A is strictly greater than x minus epsilon, okay, then the point. So just we will take the midpoint of these two, x and A. Okay, we will take the midpoint of these two. So this will be a point inside the set AB. Okay. So if A is greater than x minus epsilon, then the point x plus, or say a plus x by 2. Okay, this belongs to a plus x by 2. So this is the point inside this interval x minus epsilon to x minus epsilon intersection with AB. AB difference singleton x. Okay. So this is a point inside this set.
So this one will be x plus x minus epsilon to x plus.
This one. This is x minus epsilon.
No sir, inside this.
Intersection.
So that is x minus epsilon.
Oh yes. This one is x plus epsilon. The interval. Okay. Epsilon neighborhood. Okay. So a plus x by 2 is a point inside this interval. Okay. X minus epsilon to x plus epsilon. Okay. Something like this. And this is inside. Okay. Because a is greater than this. So if I take the midpoint of this two, then a plus x by 2, this will be greater than a, so it is greater than x minus epsilon also. Okay, as a plus x by 2, this is a point which is strictly greater than a, and a is greater than x minus epsilon, and this a plus x by 2 is also strictly less than x. Okay, so it is less than b also. Okay, so this is a point which lies inside the interval AB. Okay, and is different from x because it is strictly less than x. So then the point this belongs to this. Okay. Now it may also happen that a is less than or equal to x minus epsilon. That is, x minus epsilon is somewhere here. Okay, it may happen like that. In that case, we will take the midpoint of x and x minus epsilon. So these are the only two cases we need to consider. Because once one interval is given and you take x here, so it may happen that x minus epsilon is here, or it may happen that x minus epsilon is somewhere here. Okay, these are the only two possibilities. I am not concerned about this part. Okay, because it is just sufficient to find at least one point which is different from x. So just these two cases we will consider. So if the next part is if a is less than or equal to x minus epsilon, then the point this is one x minus epsilon plus x by 2. So I am considering this situation now. A is here, x is here, x minus epsilon is somewhere here. Okay, so I'll take the midpoint of this two. So midpoint of this two is x minus epsilon plus x by 2, that is equal to x minus epsilon by 2. Okay. Belongs to this interval, x minus epsilon, x plus epsilon, intersection with AB difference x. Okay. So this is a point inside this interval which lies in the set and is different from x. So in all cases, any epsilon neighborhood of x contains at least one point of a different from x. Okay. So in any case, every epsilon neighborhood of x contains at least one point of AB different from x. Different from x. So x is a limit point. So any point inside this set is a limit point. So from here, therefore x is a limit point. X belongs to derived set of AB. Derived set of AB. This is a member of this set. Okay. So every point inside this interval is a limit point. Next, we will check the endpoints. Okay. Whether the endpoints are limit points or not. So now let us check whether the endpoints are limit points or not. So again, let us take an epsilon. Also, the epsilon neighborhood. So the epsilon neighborhood. A minus epsilon, a plus epsilon contains epsilon neighborhood is of a. Contains the point. So which point will lie inside AB if I take a minus epsilon to a plus epsilon? A minus epsilon is somewhere here, and a plus epsilon may be somewhere here. So which is a obvious point which lies inside AB and also inside this. A plus epsilon by 2. Just take the midpoint of this. Okay. Contains the point a plus epsilon by 2. The epsilon neighborhood a minus epsilon to a plus epsilon of a contains the point a plus epsilon by 2 of open interval AB, which is different from x. which is different from A. Different from A. Because epsilon is positive quantity. So A plus some positive quantity, that is a different thing. Okay, different from A. So therefore, what you get? So A also belongs to, A is also a limit point of it. Okay, A is a limit point of AB. Limit point of AB. Okay. Similarly, we can show that B is also a limit point of AB. So similarly, B is also a limit point of AB. Similarly, B is also a limit point. Limit point of the open interval AB. Okay. This is also a limit point of this. Okay. Next, I have to check whether any other points can be limit points of this interval or not. So now suppose I have to check whether any point, every point from A to B is a limit point. This already I have shown. Now I have to check if I take a point X which is strictly less than A, then is it a limit point? If I take a point X which is strictly greater than B, is it a limit point? Okay, this is what I have to check. Let X belongs to real number and X is strictly less than A. So I have to check whether it is a limit point. So this is A, this is B, and X is somewhere here. Okay. So it will be a limit point if every epsilon neighborhood contains at least one point of this. Okay. So it is not a limit point if. So this type of things I have told you several times. Negation. Every neighborhood contains something. The negation will be there is some neighborhood which doesn't contain this. Okay. So it is sufficient to find at least one neighborhood which doesn't contain any point of this. So from the diagram itself you can see geometrically, if you take this midpoint of X and A, it will lie somewhere here. It is outside this set. Okay. So if we take this neighborhood X minus A to X plus A, then the point less than A. Then the neighborhood, then the epsilon, let epsilon equal to A minus X. Okay, I take this difference. Okay, I have taken this difference as epsilon. Okay, then the epsilon neighborhood. X minus epsilon to X plus epsilon of X doesn't contain any point of AB. Doesn't contain any point of AB. Because whatever points you take, whether it is the midpoint or any other point, okay, this will be X minus epsilon to X plus epsilon. So this interval will never contain any point of A and B. Because if you take Y belongs to this X minus epsilon to X plus epsilon, then you have distance between X and Y is strictly less than epsilon. So it is strictly less than this distance A minus X. Okay, so it cannot be. Distance of any point here from A is strictly less than epsilon. So it cannot be inside A minus X, inside that interval. Okay. So just from diagram itself you can see. So we have found out a neighborhood which doesn't contain any point of AB. Okay. So this point cannot be a limit point. Therefore, X is not a limit point of AB. X is not a limit point of AB. So similarly, if x is strictly greater than b, then taking epsilon equal to x minus b. Okay. If x is somewhere here, I take this difference as epsilon. Okay. Taking epsilon equal to x minus b, we see that the neighborhood epsilon neighborhood x minus epsilon to x plus epsilon doesn't contain any point of any point of yeah, this AB. Okay. So doesn't contain any point of AB. Okay. Why? Because so if y is a point here, x minus epsilon to x plus epsilon, this implies y is actually strictly greater than x minus epsilon. And what is epsilon? Epsilon is x minus b. So that is y is strictly greater than x minus what is b. So y is strictly greater than b. So y cannot be a point inside AB. No? That is the reason. As y belongs to this implies y is strictly greater than x minus epsilon. So that is y is strictly greater than b. So y cannot be a member inside this interval. Right. So the only elements inside this interval are those which are lying between a and b. So that means this x also cannot be a limit point. Therefore, x is not a limit point. So no number greater than b can be a limit point. No number less than a can be a limit point. Not a limit point of a. Okay. So what are the only possible limit points? They are closed interval AB. So the derived set of of open interval AB is actually what? Closed interval AB. A is also a limit point, B is also a limit point, and everything inside A and B is also a limit point. So its derived set is closed interval AB. Okay. So exactly similar way you can also justify. So derived set of closed interval AB. What is that? That is also closed interval AB. Derived set of closed interval AB is closed interval AB. Okay. Similarly, derived set of left half of an interval AB. This is also closed interval AB. Everything is a limit. And derived set of left half of an interval. Sorry, right half of an interval. This is left half of an interval. This is right half of an interval. Is also AB. Same reasoning. A is a limit point, B is a limit point. Okay. Anything less than A is not a limit point. Anything greater than B is not a limit point. So derived set of this is also this. Okay. So what is the derived set of the set of rational numbers? What are the limit points of the set of rational numbers? Derived set of Q. Derived set of Q. The set of rational numbers. So, what do you think? What are the limit points of this set? 5. Now 5 is to na. If you take a rational number, say Q, and consider any Q minus epsilon to Q plus epsilon, then this Q minus epsilon and Q are distinct numbers. No? Between any two distinct real numbers, there exist infinitely many rational and irrational numbers. Okay? So that is actually the density property of R. Okay? You take any two real numbers, between them there are many rational numbers, many irrational numbers. Okay. So even though the numbers may be very close to each other, okay, maybe something like 0 and 0.00. If you can writing zeros, and then you write 1. Okay. Between these two numbers also, there are infinitely many rational and irrational numbers. Okay, so whatever open interval you take, or whatever epsilon neighborhood of Q you take, it will always contain points which are different from Q. Okay. It will always contain rational points which are different from Q. So every point, every real number is a limit point of Q. Okay. So derived set of Q will be the set of real numbers. Okay. The derived set of Q is R itself. So how to justify this? Let x belongs to R be any point. Then and epsilon greater than 0. Then by density property of R, the epsilon neighborhood x minus epsilon to x plus epsilon of x contains infinitely many rational and irrational points. Infinitely many rational and irrational points. Irrational points. Irrational points. Okay. So x is a limit point. X is a limit point of Q. Okay. So therefore, every real number is a limit point. Every real number is a limit point of Q. Number is a limit point of Q. Is a limit point of Q. Okay. So the derived set of Q is actually R. Therefore, derived set of Q is the set of real numbers itself. Clear? Derived set of Q is R. Okay. Next is how to define closed set. Closed set. The set F subset of R is said to be closed. If it contains all its limit points. It contains all its limit points. And that is said to be closed if it contains all its limit points. Points which are very close to the set are actually inside the set, and then the set is said to be closed. Okay. For example, closed interval 1, 2. Okay, this is a closed set. It's closed. Okay. Why? What is the derived set of 1, 2? Just now we have seen derived set of any closed interval is closed interval. So this is a subset. Derived set of this is a subset of the set. So it is a closed set. Okay. But Q is not closed. Why Q is not closed? Q is not closed. the set of rational numbers is not closed. As what is the derived set of Q? It is R. Okay, so this is not a subset of Q. Okay. If the derived set is a subset of the set itself, then it is called a closed set. Okay, so our Q is not closed because derived set of Q is R, which is not a subset of Q. Okay. So Q is not a closed set. What about the set of natural numbers? N is closed. Why? N is closed as the derived set of N. Last time probably I told you this is 5. 5 is a subset of N numbers. Okay. So any set which doesn't contain any limit point is always closed. Okay. So derived set, any finite set is closed because derived set of any finite set is 5. Okay. So D of N is 5, which is a subset of N. So this is a closed set. But this is not closed. Say open interval 0, 1 is not closed. So why? As the derived set of open interval 0, 1 is equal to closed interval 0, 1. This is not a subset of 0. So open interval 0, 1, it is not a closed set. This is not a closed set. Similarly, this is also not closed. Right half open interval, this is not closed because its derived set is larger than itself. Okay. So that is not closed. So there is another definition of closed also we will do now. A set is closed if and only and there is some relation between closed and open. A set is closed if and only if its complement is open. We will do it as a theorem. Excuse me. So the next theorem that we will write is a set is closed if and only if its complement is open set. Characterization of closed sets. Theorem. The following are equivalent. Number one, A is closed, or say F is closed. F is closed in R. Number two, F complement. F complement is open in R. And F is closed in R. If F contains all its limit points, then F complement is open. Okay. And if F complement is open, F contains all its limit points. Right. So both of them can be taken as definition of closed sets. Okay. One definition is a set is closed if it contains all its limit points. Okay. It is closed in R. That is, F contains all its limit points. Contains all its limit points. Limit points. And another definition is F complement is open. Okay. A set is said to be closed if F is its complement is open. So how do you show this? Okay. So let us try to prove it. Okay, how to prove this type of things. So here there are two parts. You have to assume this and you have to show this. And another part is you have to assume this and then show this. Okay. So it may happen that in exam you get only one part. So that a set is closed if and only if its complement is open. Okay. So in that case you have to suppose this and prove this. It may also happen in the exam you are asked show that a set is closed if and only if it contains all its limit points. Then you have to suppose this and then prove this. So first let us try this. We will try to prove 1 implies 2. Okay. So let F contains all its unit points. Let derived set of F contains all its unit points means derived set of F is a subset of F. The derived set of F is a subset of F. Okay. So it may happen that the derived set is 5. Right. That's not a problem. So I have to show that F complement is open. Okay. So to show that F complement is open, I have to show that for every point here there is an interval epsilon neighborhood which is inside this. Okay. So if F complement is phi, then F, what is F? F is R, which is open. So if F complement is phi, then there is. So let F complement is not equal to phi, and let X belongs to F complement. Okay, be any point. Let X belongs to F complement be any point. Okay. So this means that X doesn't belong to F. Okay. X belongs to F complement means X doesn't belong to F. Okay. So from here I can write what? See, derived set of F is a subset of F. So if X is not in F, it cannot be there in derived set of F. Okay. So from here I can write X doesn't belong to derived set of F. Okay. Since derived set of F is a subset of F. So if X is not there in the larger set, it cannot be there inside the subset. Okay, so that means what? X is not a limit point of F. Okay, X is not a limit point of F. So not a limit point means there exists an epsilon neighborhood of X such that this X minus epsilon to X plus epsilon intersections with this. This epsilon neighborhood doesn't contain any point of F. Okay, so their intersection with F difference singleton X is phi. Okay, that is the. If it is a limit point, then every epsilon neighborhood should have non-empty intersection with this. So here it is not a limit point. That means there is a neighborhood which has empty intersection with F minus X. Okay, but you see that this, what is F minus X? F minus singleton X, what is this? X is not a point inside F. That means F minus singleton X is same as what? F only. Okay, because X is not there inside F, so we cannot remove any point from F. So F minus singleton X is nothing but F only. So this implies X minus epsilon to X plus epsilon. This intersection with F is phi. Okay, since X doesn't belong to F. Okay, so removing X from F is equivalent to removing nothing from F. Okay, so this intersection with F is phi. So if this intersection with this is phi, what can you say? This X minus epsilon plus X plus epsilon, this will be a subset of what? This will be a subset of F complement. Okay, A intersection B is phi. Okay, this always means that A is a subset of B complement. Okay, right? Means there is nothing common between A and B. So all points of A, none of the points of A is in B. So that means all points of B, A is in B complement. Okay, that is the standard result of set theory. This intersection, this is phi. That means this is a subset of F complement. Okay. So ultimately, what I have got is, but X is a member of this. So X belongs to X minus epsilon, X plus epsilon, which is a subset of F complement. Okay. So given any point inside F, given any point inside F complement, we have found out an epsilon neighborhood which contains X and lies completely inside F complement. Okay. So this satisfies the definition of what? Open set. Okay. A set is said to be open if for every X inside that set there is a epsilon neighborhood which contains X and is inside the set. Okay. So from here we can write, since X is arbitrary, so so F complement is actually open. Okay, F complement is open. Okay. So we have proved. F complement is open. Proved. Okay. This part is proved. Another part is 2 implies 1. Okay. If F complement is open, we have to show that F contains all its limit points. Okay, so the other part is also simple. 2 implies 1. Suppose that F complement is open. 2 implies 1. Let F complement be open. So that F contains all its limit points. Okay. So it may happen that the direct set of F is phi. So if direct set of F is phi, then direct set of F is a subset of F. Obviously. So let direct set of F is non-empty and X belongs to direct set of F. Be any point. Be any point. When X is a limit point of, this implies X is a limit point of so we have to show that X is a point inside F. Okay. So if X is not inside F, then what will happen? Okay. We will do it that way. And then we will show that X has to be inside F. Okay. Just quickly we will do it. If X doesn't belong to F, okay, then X belongs to what? F complement. Okay. But F complement is open. F complement is open. So there exists epsilon greater than 0 such that X belongs to X minus epsilon to X plus epsilon, a subset of F complement. Just the definition of open set. If X is not there in F, then X is there in F complement. Okay. But F complement is open. So there exists an epsilon greater than 0 such that X, this epsilon neighborhood is a subset of F complement. Okay. Then just we will go reverse, just like the previous one. Since this is a subset of F complement, this means that X minus epsilon to X plus epsilon, this intersection with F is phi. Okay. Right. So this is an epsilon neighborhood of X which contains no point of capital F. That means X cannot be a limit point. Okay. So X minus epsilon, X plus epsilon is an epsilon neighborhood. Is an epsilon neighborhood of X which contains no point of F. Okay. If it is a limit point, it should contain at least one point. Okay. But here it doesn't contain any point of F. It contains no points of F. Okay. So therefore X cannot be a limit point. But already we had X as a limit point, so we can write. So therefore this contradicts that X is a limit point. X is a limit point. This contradicts that X is a limit point of F. Okay. We had started with X is a limit point. Okay. So where was the problem? The problem was here. if x does not belong to f. Okay, if x is not there in f, then we get a contradiction. That means x has to be there in f. So, if x is there not there in f, there is a contradiction. So x has to be there in f. Okay. So this contradicts that x is a limit point of f. Hence, x should belong to f. Okay. So therefore, the left set of f is a subset of. The left set of f is a subset of f. Right. So this is the equivalent criteria. So a set is closed if and only if it contains all its limit points. A set is closed if and only if its complement is open. So sometimes this definition is useful. Sometimes this definition is useful. Okay. So there are some more results. Union of closed sets, intersection of closed sets. Okay, that's what we follow. Okay, so almost we are done with this paper. So the next class will be